Ma'am, we would wait for some time, like let other people join, and then we would start.
Okay, that's fine.
Mhm.
Well, while we're waiting on other people, would you like me to introduce myself or anything?
Um, Ma'am would give a formal introduction. Before that, you may
Okay,
start.
okay. I'll I'll be patient.
Yeah. Um, okay, so let's start the session. Good evening, everyone. We are honored to have you all here, and we welcome you to this amazing workshop. And on behalf of EAGE, IIT ISM Dhanbad, I welcome you all for this. And as you see, the workshop is on advanced machine learning techniques for geosciences interpretation and explanation. And as many of you know about our student chapter, which is a vibrant hub of global activity, we had been hosting many workshops and such sessions for the students to get more exposure into the real world and the real industry so that they could be ready for the future. And we are honored to have with us Dr. Bedle, Associate Professor at the University of Oklahoma and a leading researcher in seismic interpretation and machine learning. Dr. Bedley's work with the Attribute Assisted Seismic Processing and Interpretation, AASPI as we say, consortium has been instrumental in advancing the integration of seismic attributes. And you would have all seen her lectures on YouTube on AASPI portal. It's really helpful. So without further ado, would like to start. Just a few more things for about her. Her work on DQ trace method that I had earlier also referred to is really amazing. And if you have any questions regarding the workshop, whatever she's telling you, you may post it in the chat section or you may ask after the session. And let's start, ma'am. It's
All
all
right.
yours.
Thank you. All right, so I'm going to get started, and typically with student chapters, I never quite know how basic to start. So my plan today is to just chat for a few minutes about reflection seismic, and then move into some seismic attributes, show you some cases where we've combined machine learning plus attributes, and then talk about some workflows that my students have used and we've put together, and then spend and kind of wrap up for a few minutes just talking about explainable AI and how we can use that when we're applying machine learning to seismic attribute analyses, all for subsurface characterization. So to get started, just if you are not familiar with seismic reflection data, what happens is you typically, this can be done on land or on sea, and so this diagram here, let me put on my pointer, is showing a water case over sea where you have a boat that's tugging an air gun and also some hydrophones. And what happens is energy is shot off. It travels down through the subsurface, and when it hits an interface, just based on Snell's law, some of that energy is reflected back up, and we record it. And so what we end up with, and the main kind of data set that I work with is seismic reflection data, which looks like this on the right-hand side, where you're seeing a lot of red and blue lines kind of going back and forth, back and forth. And there's a lot of details on what these actually mean, but these are showing us the interfaces of the rocks, and we can take information about the amplitude and the frequencies to give us insights into what lithologies, what fluids, what structures, what stratigraphic features may be kind of hidden down in the subsurface. So that's the data we're working with. And ideally, we would love for these peaks and troughs or features to be just like when we go out to an outcrop and look at it. But the problem we have is that with seismic data, because of the frequencies we're working at, we're typically only able to resolve boundaries or interfaces of beds that are 10 to hundreds of meters thick. So we don't get the same detail that we would in looking at an outcrop and doing an outcrop study. And so this data has been around, this method's been around for over 100 years. And back in the 1970s, we mostly had 2D data. I was born in the 70s, but I wasn't looking at seismic data back then. And you may have heard of the methods of classical seismic stratigraphy. And so this is looking at that 2D data that is kind of like an outcrop. And you could look at the different patterns and identify different stratigraphic features like onlap, downlap. We've got erosional truncation in the data. But as we moved into the 1980s, and now is very common, we have three-dimensional seismic reflection data. And so now we're able to do seismic geomorphology studies where we can look in the third dimension. So we can map out horizons. We could look at time slices as well as those vertical slices. And so a lot of what we're doing with seismic geomorphology is trying to recognize patterns. So we're looking for patterns in the seismic data that we as geologists can identify as, oh, that's a channel system. Oh, I see some gullies. I see faults. So what we're doing is pattern recognition. And this is where we use seismic attributes. So seismic attributes aren't anything more than just math. They're different algorithms that we apply to the seismic data, maybe to focus on changes in amplitude, changes in frequency, and all of these we can relate back to lithology or fluid properties. And so the good seismic attributes tend to be sensitive to those geologic features we're trying to map or understand, or maybe a reservoir property of interest like porosity. And so these are very commonly used. There's probably way more than 50 seismic attributes. There's hundreds of them, I'm sure. And all of them have different purposes and can be used in different ways. And so in interpretation, when we're going out as geologic interpreters, we'll often use multiple attributes to help us see those patterns so that we can interpret them. So this is a classic example I like to show from Chopra and Marfort's textbook, where over on the left-hand side, we're looking at a time slice. So we're just looking, at a certain time in depth. And we can see that there's, some features, like I've looked at this a zillion times. So I would, think that there's probably some channels or faulting going on. I see, you know, lineations, I see changes in color. But if we took just a few minutes to run the coherence attribute, which is an edge detector, we can very quickly get this image on the right-hand side, which shows us a lot of very overlapping individual channels. So you can imagine if you're interpreting this, you would have a lot more confidence and lower uncertainty in your interpretation when you use the seismic attribute. And so this is why I love seismic attributes. Like was mentioned, I have a lot of information. I've been really working the last year to record a lot of my lectures and all sorts of other types of videos up on YouTube. So if you go to my AASPI webpage at OU, and I'll have the link on the last slide, you can find all of this information that I'm talking about. And I'll also mention that we have the AASPI training course. And if any of you want to try out AASPI for a few months, you can just shoot me an email and I'll send you a demo license, which should work for a few weeks or a few months. Might be something fun to do over the summer. Try it out. On our data, we have some demo data on the website or on your own data. So just send me an email, let me know you were in this lecture, and I'll get you set up. Okay, so anyway, so I greatly encourage you, if this interests you or if I didn't cover something enough in this hour, you can go on the website and find more information. All right, so let's look at some seismic attributes. Like I mentioned, there's dozens, hundreds of them. I'm just going to talk about a few just to give you a little bit of insight. And I'm going to focus on the geometric attributes, which are often the ones folks start out with and kind of the most useful in a lot of cases. And so the reason I really like AASPI's attributes, so most software programs, you might be using Petrel, they have attributes built into them too. But I have found, and I mean, we're a research group, so we don't really sell our software, that AASPI's algorithms often have much clearer images than you would get with some other software programs. And this is because we use a very rigorous dip calculation to calculate our attributes along, and I'll show you an example of that. We also have really been expanding into machine learning the last few years, and so I think we have probably over 24 different machine learning algorithms embedded in our software, and you could try this out on the demo version if you want. From unsupervised to supervised, random forest, we've got convolutional neural networks, probabilistic neural networks, so there's a lot in our software where you could take the attributes you calculate and just apply it. And of course, we have like spectral, all the spectral attributes too in spec-decomp. So to get started, the first geometric attribute that we always calculate as soon as we open up AASPI or for any study is dip. And I mentioned that that's because we want to use dip as a basis for calculating a lot of our attributes. And so all this is a very rigorous, we have different dip calculations, and I'm not going into the details of the different ones here, but you could shoot me an email later if you want more details. But there's different ways you can kind of move through the data and search for dip. And so we run dip, essentially we are trying to find where for one analysis point we have, as we move from trace to trace, we have the maximum coherence. And so in this case, it's 5 degrees just for this example. We can display dip, we can display the azimuth of dip, the magnitude of dip. All of this gives us great structural information. These images that I'm showing in this part of the lecture are from the Great South Basin, which is just east of the South Island of New Zealand. And so it has some great features, some channels, some very small scale faults, some larger faults. And so this is just what dip would look like at a time slice of 1.28 seconds. The different color gives us the direction. So the blue colors are dipping to the north, the yellow colors that are dipping to the south at that point in space. And then the magnitude, we use an opacity mask. So higher magnitudes appear brighter, lower dip magnitude, so it's not dipping very much, are kind of grayed out. All right, once we have dip, we can calculate coherence. And so coherence, Again, there's many different algorithms and ways you can calculate coherence, from how many neighbors you compare it to your how much of a time variation time you're looking at. I apologize, it's the morning and I'm still waking up, but but so there's a lot of different parameters that you could test. In this case, I'm just trying to show, we may be comparing this pink waveform to ones in the crossline direction or the inline direction. You could also calculate them in just one direction or the other. And the reason we use dip is so that we can, on this right-hand side, you'll notice that we're dipping at a few degrees. And if we calculated it straight across, it would look very different. And so when you can account for dip, you get a much clearer coherence image. And so looking to this next slide, this is just a simple calculation of coherence. It's an edge detector, so we can see very clearly, very quickly, a lot of faults in this area. It would be very easy to map them out at this point. If you want to look at the curvature, that's another very popular, well-used attribute. Curvature is telling you how curved a surface is, and it's actually the first derivative of coherence. So if you have a flat plane or a dipping plane, your curvature, which we abbreviate as K, is 0. If you have a syncline, it's negative, and if you have an anticline, it's positive. And so this has been really good for small scale features. Like even small scale fractures and also for seeing the edges of channel systems if you have levees built up or the axis of the channel. So it's a great geometric attribute. And looking at it on the time slice, we can see the image right here where the positive curvature is red, the negative is blue, and so you can actually see some of that dragging associated with the upthrown and downthrown side of the faults that we saw in coherence. Shape index is another fun attribute to play with, and the shape index is just, I have the equation up here, but it's just a combination of your most positive and negative curvature calculations. And what you can do is you can get a little bit more detail about specific shapes. So you can see here on the right-hand side, I've got in blue kind of a bowl shape feature. Down at the bottom, we've got a dome in red. We've got some ridges, some saddle shapes. And so depending on how the positive and negative curvature at any point, you can calculate the shape index S. And you can map out your bowls, your valleys, ridges, domes. And so this would end up looking like this in a time slice. So here we're looking at the same data. We've just moved a little bit deeper where we have a lot of synuresis features. So you kind of sometimes see synuresis on sidewalks where you have mud that cracks. And so we've got a lot of bowls and a lot of domes kind of overlapping each other, and they look like these little dots. And what's kind of neat is you could actually go into another software program. So here Kurt did this with Petrel, and he made geobodies and co-rendered the shape in color with the coherence in the grayscale at this time slice. And so you can see some of those synuresis features and how you get the geobody associated with the bowls and the domes. So just a nice visualization, really gives you information about your seismic data. And so we've talked about coherence, we've talked about curvature, and one of the newer attributes that we've been using the last 5 years, and we've found really good for looking at basement faults or smaller scale features, is called aberrancy. So aberrancy is the second derivative of coherence or the first derivative of curvature. And what it shows you is kind of where you may have a little bit of fault offset that's below resolution. So you don't have enough of a clear cut difference that coherence would pick up on it, and it may be a little bit too subtle for curvature to pick up on it. But aberrancy will see just that very, very subtle offset. So in seismic horizons, it may look a little bit like a dip. And so just to show you an example between aberrancy and coherence, here's coherence, the same time slice we looked at a little bit earlier. And we've got a couple of interesting features here that I'm pointing out with the yellow and the white. You can see a nice fault offset in yellow. We've got clear faults down here in the southern portion. And then in white, I'm picking up some features that we're getting hints of in coherence. But when we run aberrancy, we can see them, there is on there, much more clearly. So these are additional faults that coherence wasn't picking up quite as confidently because the offset wasn't, it wasn't a clear-cut offset where the edge detector would work. And similar to dip, aberrancy shows us the direction. So we've got the total aberrancy azimuth as well as the magnitude of the total aberrancy. And so those are a few geometric attributes I wanted to talk about. And then the last one to wrap up before I go into some machine learning case studies is multispectral coherence. So many of you, if you've done any work with seismic interpretation, you may have heard of spectral decomposition. And so with seismic data, you can separate out different frequencies, and then you can sum them together. And often we see spectral decomposition with channels and stratigraphic features. But you can do a similar technique with geometric attributes. So in this case, we're taking different spectrum with coherence. Okay, and so it's just breaking it up into the spectral components, running coherence, and then summing them back together. And of course, things look better, more visual. So this is an example from one of my previous master's students. So we're looking at these faults in the Oklahoma basement. So Oklahoma, it's kind of in the center of the United States. We do a lot of wastewater disposal in Oklahoma from all the wells that are drilled, and it's started to trigger maybe 10, 15 years ago, small scale earthquakes. So we're interested in seeing these small faults so that we can avoid them when we're injecting. And now as we're talking about injecting for carbon capture, it's also important to be able to understand where injection may be a little bit riskier. So anyway, that's the background geology of the study. But so what we've got here are a couple of different horizons from the top Arbuckle, which is the main injection formation, to the top of the basement, and then an area a little bit deeper where there's some interbasement reflectors that we're able to pick up. And she's mapped these out in broadband in the grayscale on the top, and then multispectral coherence on the lower level here, where she's done a red, green, blue overlay, just like we would do for spectral decomposition of our raw seismic data at 38, 49, and 60 hertz. And so in some cases, you're able to see these lineations a little bit differently, a little bit more clearly when you combine different spectrums. And we found this works with faults, with stratigraphic features, and there's a few different studies up on my website that use multispectral coherence. And there's no reason you can't do multispectral curvature or aberrancy or any other geometric attribute in a multispectral sense. All right, so now I want to talk for a few minutes about some case studies. So I'm not going to go into detail about specific machine learning methods with attributes, but I thought as students, if you're interested in applying these, you might want to see how I coach my students to work through a workflow. So I'm going to do two different case studies. The first one is looking at deep water channel architecture. And the second one is in deep water Brazil in the Santos Basin, looking at carbonate and volcanics. And so I'll just get started. But this is the first case study. It was done by my PhD student, Corellia Lamarca, who's working with BP now in Houston. And this was part of her, I think, master's project. So the first project she did with me. And we're working in the Taranaki Basin. So one of the things I always tell my students is to start off thinking about where you're working, what's the geology, what would you expect to see? And so the Taranaki Basin, New Zealand's data, they make a lot of it public. Their well data, their seismic data. So we often do a lot of academic studies with New Zealand data. Plus the Taranaki Basin is very well studied. And so in this case, she's using the pipeline 3D data set. And we've got one well to use for correlation purposes. And so in this study, the first thing is to understand the geologic system. I find that as a geophysicist, you can be a much better geophysicist if you understand the geology of what you're trying to image. And so step one, I always tell the students, what features do you anticipate in this system? So go and do your literature review. Try to understand the different architectures you may find. And so this is just a image from a paper that Corellia was using as one of her references to try to show the variety in deepwater architecture, from erosional channel belts that may have differential channel fills. You can have meandering channel belts, which will look much different in cross section, so vertical section, than they would in a time slice or horizon map. You can have large channel belt complexes. You can have levees. There's deepwater channel architecture is fascinating. There's a lot of variations you could get. So just looking at cartoons like this can really help ground you in what you should expect to see in the seismic data or the possibilities. So then I like to have my students do a little bit of a thought experiment and often make a table similar to this, where they go through the different architectural elements or features they expect to see in their study. Have maybe a little cartoon of the geologic scheme, and then think about what would be the reflection configuration. So it sounds kind of a little philosophical maybe, but I think it's good to think about, all right, what shape would we expect these features to have in the seismic? Would they be parallel or subparallel reflectors? Would they be chaotic? And if you have a large enough feature, you will have a different internal seismic configuration than the external shape of it. So you have the external shape of the larger channel system with different internal structures in it. You would have variations in the amplitude, so I often have them think about that. And then in this case, she also made a little visual of what the vertical slice would look like through this architectural element as well as the time slice. And so all of this is just trying to ground you as an interpreter into how to see the seismic and how to pick up more clues. And so we've got over here on the right-hand side a time slice, um, where you can see she's picked out a channel belt, got a little bit of a question mark there. There's some sinuous features. There's obviously a bit of dipping going on because we're crossing a lot of seismic horizons. And then looking at it in vertical slice, particularly with the well for reference, she's picked out some channel belts, some possible levees, erosive surfaces. So all of this, as you look at this, you can kind of be like, yeah, I could believe that. I can believe those interpretations. But of course, this isn't talk about seismic attributes in machine learning. So the next thing to do is to think about, okay, with all of these features, what different attributes may be helpful? So a lot of software programs, including AASPI, you could go in and run 100 seismic attributes, but you do not want to spend time interpreting 100 different seismic attributes. It will take you years to do it well. So I often like to think about, okay, what am I expecting? What do I see in seismic? Now let me choose 5 to 10 seismic attributes to start off with. And so in this case, Corellia went through that thought experiment and chose a few different attributes, kind of put down her thinking about why she thought they would be useful. So most of my students all do this. Okay, so she's picked out her seismic attributes. The next step is to examine each attribute individually. So in this case, I'm just focusing on 4 of them. So we've got GLCM entropy, which is a textural attribute, kind of comparing the texture of what's going on at one point in space to next to it. We've got RMS amplitude here in B. We've got Sobel filter, which is a type of coherence, an edge detector. And then we've got a spectral decomposition, so the continuous wavelet transform algorithm with 13, 35, and 60 hertz. So these were 4 of the ones she found most useful. Of course, she understands the principles behind them and their geologic use. And you can see, just comparing this mentally to the time slice in the previous page, we're getting a lot more detail. So coherence, or the Sobel filter, is showing us these larger scale channel bodies. We're even seeing some minor channels that are pointed out by the pink arrows. You can see variations in the amplitudes. We've got some sediment waves kind of in the middle of all of these time slices. So a lot more that now as geologic interpreters we can point out in our seismic. Now that we've got a lot of seismic attributes, I often talk about, we could co-render 2 or 3 of them together, but if we have a half dozen or more, we may want to use machine learning. And so in this case, we're using an unsupervised machine learning method called self-organizing maps, where there's no guidance from the geophysicist or yourself, but rather you're letting the algorithm identify in color different areas that are similar to each other with all of the different attributes that you put into it. And so I like showing this image to students because it's not like machine learning isn't magic where you put a bunch of stuff in and you get a definitive answer. So in this case, we've got 3 different SOM results that used 3 different sets of seismic attributes. So you can see in SOM 1, there were 4 attributes, SOM 2, there were 5, same with SOM 3. And what you'll notice is that when you compare these, whether you're looking at the time slice or her interpretation, you can see that the large scale features all appear similarly, but looking at different SOM results can give you different insights. So a lot of these kind of splays appear a little bit more clearly in SOM 3 than they do in SOM 1. And let's see what else is a little bit different. The sediment waves, I think, show up also much more clearly in SOM 3 than SOM 2. So you could spend a bit of time kind of comparing and contrasting these. But I just want to make the point that you'll often have to run different variations of your attributes into these machine learning algorithms to get a good result. And so when you look at it compared, I've put up on the screen the original time slice, suddenly you can see how as an interpreter you can be much more confident when you employ seismic attributes and some of these very basic machine learning algorithms, which are just kind of like statistics amped up. All right, so once you have your SOM results, you can, move through the seismic data just like you would a regular seismic volume. You can see how the system evolved, and this was part of her research, was kind of trying to understand the evolution of the system and some of the elements. So this is just kind of showing through different time slices how this Moki formation and the channels related to it evolved through time. So that was kind of the geologic purpose. And then she ended up combining a couple of different SOM results in a more clear figure here, where she did more detailed interpretation, trying to map out the scroll bars and using all of this as a tool for her geologic interpretation. Okay, so I'm going to show you one more example really quickly. This is one in deepwater Brazil. So we're looking at some offshore carbonates and volcanics. And most of this work has been published. It was kind of a 3-part series for Marcus's PhD, and he just graduated. So we're, the 3rd paper's in review right now. So we're offshore Brazil. We're in the Santos Basin. And using some data from Petrobras, we have a lot of seismic data, a lot of wells. We even have production data. And so this was part 1 of his, or part 2 of his PhD. But there's some interesting features where you have igneous bodies that have had carbonates build on them. They've been the porosity has been increased through hydrothermal venting, and there's some really great production reservoirs in this area. So Petrobras, who Marcus works for, wanted to know if he can use machine learning to move from one field where they have a lot of data to other exploration or frontier fields that they were scoping out. And that was kind of the arc of his PhD. And so again, I wanted to step through this just like I would show a student how to step through it. But the first step is, of course, getting your data, doing some QC, adding in your wells, cropping it to your area of interest. And so that was kind of the first thing that Marcus did here. You can see there's a platform up here, which has had a lot of wells drilled into it. For machine learning, he used some of them for analyses, and other ones he left for testing and validation. So that's why some of them are called X. Those were the test and validation wells. All right, so we've got our seismic data, we've cropped it. Again, he researched his attributes. So the same thing I had Corellia and most of my other students always do, thinking about the different attributes, what seismic facies would they help you see? What would be the seismic signature? What's the geologic reason for using that attribute? And so he put together his chart a little bit differently than Corellia did, but all of that information's in there. So a lot of times when I've worked, I spent about 10 years working at Chevron, and a lot of times you have to convince your engineers or your project manager why you're using these attributes. And doing, like a detailed analysis like this can really help give confidence to your teammates or maybe your advisor that you should be using attributes in machine learning. Workflows are also a very important step that I spend a lot of time on when I'm talking to students and they're going through their research. And so I find the better we can outline the workflow to begin with, the more efficient the student moves through their projects. So don't overlook, building these boxes. It's kind of boring to put it together, but we'll spend a lot of time on this workflow step. And then it's also great for when you're writing up your research later on, that you have a clear workflow to talk about in your paper dissertation. And so this is just a summary of Marcus's workflow from inputting the seismic data to the calculating the seismic attributes. He did some normalization, which can be very important when you're taking attributes with different scales and putting them into machine learning methods. And in this paper that I'm showing you, he was using unsupervised machine learning methods. So self-organizing maps, generative topographic mapping, and then k-means. And so I'll show you a comparison of a few of them. And then since he had well data and production data, he could compare the different clusters from machine learning to the results to understand what kind of colors in the SOM output might be other highly productive areas. Okay, so got the workflow. Here he's looking at all of his different attributes. So he ended up using 9 attributes or so, 9 or 10, I believe. A lot of the GLCM attributes, those texture attributes. He did a Hilbert transform. He had velocity in there as an attribute, similarity, let's see, curvature also. So different attributes that he found useful. You can see here he's interpreted them as different mounds or buildups, trying to highlight, okay, this attribute is definitely giving us information. So when we put it into the machine learning algorithm, it's not just magic that we're expecting. In step 5, like I mentioned, he ran several different machine learning methods. So in Corellia's work with the channels, I showed you 3 different variations of SOM. Here Marcus has 2 SOM methods as A and B with different attributes in them. And then we have GLCM as C and the k-means results are as D. And what he was able to do is tie this 2-dimensional color scale to different seismic facies. And this he could do very confidently because of all the well log data we had available to us. So again, it's interpreting and then making sure that you can prove what these colors mean in the machine learning algorithm. This was one of the, okay, so this is showing in a horizontal section. Okay, so we're going through a row. We've got the input amplitude with a well, the SOM results, the k-mean results, the GTM results, and then you can see the well log over here on the far right. And so these are just other ways he worked through the data from wells, well C, X4, X3, just kind of correlating everything to what he's seeing in the machine learning bases. So that he could kind of prove up and say, okay, I think this blue is a buildup that could be highly productive. And then down here, they have one on the bottom row. We have one of the leads that they were looking at and trying to assess to understand if that would be a good place to drill a well. So again, just different ways to look through the data and validate your machine learning results. So after doing that with the wells and having confidence in your models, you can then look at the entire volume. In this case, he used Petrel and some masking in order to highlight the areas he was particularly interested in. So you can, and also creating geobodies. So you can see in this upper left-hand case are the igneous intrusions and where they're appearing in this formation of interest. More of the buildups and mounds, which were highly productive, are being shown in B over here, particularly in this area more towards the east that they were evaluating. So again, different ways to work through it to kind of get your results out and interpret. And so those were two quick cases. And what I wanted to kind of end up with is a quick discussion of if we should trust seismic facies models. And so this, I'm going to try to go through very, very quickly in a few minutes, but I'm happy to talk about it more offline or point you to some other results. But hopefully you got a sense of, in a lot of what we do, we're taking our seismic attributes, kind of calculating them all, we're kind of throwing them into this machine learning model, which is a bit of a black box, and then we get a result. Okay, and so the motivation for this part is, can we make machine learning models for seismic facies more interpretable, more trustworthy for geoscientists? So you may have noticed that so many people are using machine learning nowadays. The tools are so easy to use. We have to really focus on critically analyzing what's going on, like especially if we're going to spend millions of dollars to drill a well or devise whole new scientific hypotheses based on machine learning results. And so when we think about the way machine learning models work, in this case, they typically learn a set of rules. So it might be from statistics, and they're applying it in this multi-attribute space. So in this case, I'm just trying to show a quick example. I have a voxel, I've calculated some attributes. So in this case, total energy. If the total energy is high, it might be a turbidite or a channel. If the total energy is low, maybe a background shale or a channel. And then as we add in more attributes for that same voxel, we can kind of get to a solution. And so understanding this logic of what's going on in the machine learning models can be very important for understanding the uncertainty in the models. So I want to talk about for a few minutes some different ways we can think about machine learning results. So I'm going to show really quickly vector plots, LIME, SHAP. Some of my students are also looking at evaluating partial dependence plots, accumulated local effects, so PDPs and ALEs. There's a lot of methods out there that you may have seen that are trying to help us kind of peer into that black box. So I'll talk about a few of them. So vector plots is a tool that we've had built into AASPI, and it's in a lot of other softwares. I wouldn't say it's really looking into the algorithm, but rather it's helping us understand what's going on. And so this is just a query tool where for any voxel, we can look at the values of the different attributes. And so it's very simple. We've had it for years. I think a lot of the softwares, you could do the same thing. So like if I hovered over the voxel with this, where this yellow star is, I could see that my curvedness was 0.36. I had a very high GLCM entropy. So it's just giving me insight. So I could go to the classifications and see if there's any patterns. Of course, this takes a lot of time and mental effort for me to go through the volume and understand, okay, what attributes are high or low when it's a channel. So it's not the easiest one to use. Rather, we want to try to get back at this logic. And so this is where LIME and SHAP are good methods to use. So I'll talk about each of them really quickly, and then I'll show you the examples. But with LIME, these are local interpretable model agnostic explanations. LIME and SHAP can both be applied to a lot of different machine learning algorithms, and you may have already come across them. The main difference between, the main thing with LIME is that it's local. So it's explaining one decision at a time, so one voxel at a time, not the whole model. The model agnostic part of the name is because it could work with a lot of different AI models. And so the explanations it can give you can be intuitive to yourself as a geologic interpreter. So like in this case on the right-hand side, I've got my channel marked by this purple voxel, and I could see that it has a low peak peak magnitude, higher GLCM homogeneity, coherent energy, etc. And so it's pretty good for understanding. SHAP is my favorite. I won't lie. Right now, it's my favorite. Um, and what SHAP does is it can look at your decisions locally, but also globally. And I've found the global aspects to be incredibly helpful. So locally, at that same purple star, I can get an idea that the K-curvedness was high, the peak frequency was high, coherent energy was high, and so all of that add up to it being classified as a, I forget what purple was, a channel. But I could also look at what do channels look like over the entire model, and I could see that GLCM homogeneity for all the different points in my model are low for channels and high. Uh, if they're low, they're not a channel. If it's high, it is a channel. So, you know, being able to understand what's going on locally for one voxel and the entire model itself for an entire seismic facies can be really important. So I'm going to quickly show this applied to the WACA 3D data set, which is also off the South Island to the east of New Zealand. And it's an interesting area. It's got a lot of really great channel systems. In this time slice here, you can kind of get a hint in the seismic data from some of those channels. But of course, attributes will help us more. So thinking about the methods as I go through this study, you know, I've got my data preparation, so identifying the target facies. I'm using random forest in this case. So in this case, I classified. So I picked out parts of the seismic and said, this is a turbidite, this is a background shale, this is a channel complex. So after identifying my target facies and figuring out which seismic attributes to use, I prepared my random forest classifier, you know, getting some of it set aside for training, some for validation. And then I'll show quick examples of these three different explainable AI techniques, because the point of the study was to kind of understand them. And then, you know, you can compare and contrast them. You can understand where the model didn't work and use explainable AI to improve your interpretation. So in AASPI software, we can just kind of create polygons. You know, I'm just showing here a polygon for background facies. Here's one for channel facies and for turbidite facies. And then from that, I've got my 6 attributes that I was working with. So just showing you a quick example of all of those, again, and why I use them. And then the random forest results, which we've kind of been seeing in the last few slides anyway. So at this time slice, I've got turbidites in green, the channel in pink, and you could see there's a whole lot of pink, which is not channel, and then the background in orange. So as an interpreter, I may want to understand, okay, what went wrong? And so I've got this AOI here marked by the blue star where I'm trying to understand, okay, to me, that looks more like a channel splay, which I didn't classify. But let's try to understand between these 4 points what the difference is. And so with the vector plots, I could look at the value at each voxel and I can get an understanding of, okay, you know, in this case, the channel and the background seem pretty similar, and maybe that's why AOI, that area that was misclassified as the blue star, isn't working. So again, it's a lot of hunting and pecking. It's a nice qualitative tool, very easy to use. So with Lime, again, it's local, so I can only look at those voxels, but I can go in and look at the channel, and I actually get a percentage of what's going on. So the percentage turbidite, the percentage background, you know, it was 91.6% sure it was a channel. And then I could look at the individual attributes and understand, okay, it was high, it was low, you know, there's a lot of thinking that you still have to do, but trying to understand what's going on here. And so I could get some insights. And then with SHAP, I can look at it at each pixel again. SHAP gives you the percentage. So again, it was a 1% chance that it was a turbidite, an 8% chance it was background, and it was 92% confident that it was a channel in this random forest classification. And it allows us to also look at if each attribute is building it up towards being a channel. So in this case, the values of all 6 attributes kind of pushed it towards the channel classification. All right. And so all of these were working locally, but I think the big insights kind of come more from looking at the summary plots or the global analyses with SHAP. And so this is showing the global analyses for those 3 different facies. In this case, with the SHAP summary plot, you can see that peak magnitude was very important for turbidite classification. And then it looks like coherent energy in the pink and peak magnitude were very important for background classification. So now you kind of see the weighting of each attribute and how it's going into the classification as a whole over your entire model. And so this is why I like SHAP a little bit better for my analyses, is just I'm getting an overall view of what's going on. And so I can take these insights and look at that area of interest where I misclassified. I can look at some of the seismic attributes and kind of realize, okay, well, it's really pinging on that coherent energy to classify it as a channel, but it's not a channel. I would interpret it as a geologist as a channel splay. So maybe I need to retrain the model, think about adding more attributes, or maybe even a whole new seismic facies if, I can't have this mistake. All right, so I'm going to wrap up. I've talked a little bit longer than I've wanted to. But I just wanted you to see like how you can easily use explainable AI to bridge machine learning and geology, to try to understand and dig into your models a little bit more deeply to understand the decisions that are being made. And I've got a lot of examples of this more up on my website if you want to see it applied to like probabilistic neural networks or a different method besides random forest. And so let me just kind of conclude with this. Hopefully you've seen that seismic attributes really help you see more patterns in the seismic data. You can combine them with machine learning. And then when you use machine learning, you always want to critically think about it, to understand what's going on and how it's making the decisions. So explainable AI can give us that rationale for our team members to help them understand what's going on. It can help with model transparency and kind of build your confidence in the results it's giving you. And it also is a good way for you as the human with the in context geologic knowledge to help interpret or help guide the machine learning algorithms. So with that, like I mentioned, I did all this very quickly, but there's a lot more information on the website. I've got my email here. You could reach out to me if you want to try out AASPI for a few months and just see what it does. Practice it with our training data sets or with your own seismic data. And so with that, I think I've got a couple of minutes for questions. Hold on, let me check. Yeah. So let's see. I think I can go to the chat. So you've got my email. I will say, because I just saw one point up, I'm not currently recruiting. So I am looking to maybe bring in one PhD next fall. That's all I have funding for right now. So I don't bring in students unless I can fund them. It's just kind of my policy. And I often work with students, sometimes remotely. So if you are at a program and you want to use AASPI and you want some of my guidance, like I'm always happy to help that way too. But you could always reach out to me if you want. Typically, like our funding situation has been very weird in the US with our new administration. So, it's been harder to fund students. I'll just put it that way. But yeah, you could always feel free to reach out to me and ask me questions. Like I am a professor because I wanted to mentor students and guide and do education. So,
Thank you so much, ma'am.
yeah.
Your insights were indeed valuable. You truly served a delicious blend of ML techniques and seismic attributes. So let us continue this formal chain of events. And I would like to formally conclude this session.
Thanks.
A good event leaves you inspired, and for that, we owe thanks to those who made it possible. On behalf of the European Association of Geoscientists and Engineers, IIT ISM Student Chapter, and the Department of Applied Geophysics, I extend my heartfelt gratitude to Dr. Heather Bedle, our distinguished speaker, for her valuable time and insights. Your session was truly enlightening and has sparked our curiosity about the real power of machine learning in geoscience interpretation. Thank you for sharing your expertise on SHAP explainability, the AASPI consortium's work, and your deep experience in integrating seismic attributes with ML techniques. I'm sure this talk has left all of us with new ideas and a broader vision of how data and geoscience can converge. As we come to the end of this webinar, I once again thank Dr. Bedle and all the participants for being part of GeoQuest, Advanced ML in Geosciences. We hope today's session helped you see the exciting future of machine learning in geoscience, research, and applications. Stay connected with us on our official social handles. Until next time, thank you.
Thank you.
Thank you, ma'am.
No problem. I'm just trying to see. Okay, it looks like my website was posted. So yeah, anybody can reach out to me anytime. Thank you and have a good evening.
Thank you, ma'am.